start recording and say hi. So this is lecture number 2. And today we're going to be talking all about forces and Newton's laws. They kind of go hand in hand. In that, especially at A level, the forces that you're looking at are basically governed by Newton's laws. So we'll start there and then we'll kind of go backwards into forces. And then I've got a few exam style questions for us to go through that have the classic tropes, the light and extensible strings, the inclined planes, all that jazz. I tried to pick some interesting ones for us to do. So as with everything in maths, eventually we have to mention Isaac Newton. So there are 3 laws attributed to Newton. Check that's a good one. Where the webcam is. Perfect. So, so the 3 laws attributed to Newton that govern motion. Specifically 4 things that. So Newton's laws only apply for things in sort of the Goldilocks size. So nothing that's like huge. So if you listen to the Unstable Fluid podcast where I chat with Thomas Rintoul a lot, he's an astrophysicist. So these laws start to break down when you start looking at like galaxies and stuff. Some of them apply if you make enough assumptions, but typically nothing too big. Doesn't really work on the small, very, very, very small scale as well. So nothing sort of quantum size or atomic size. So not too big. Small. And specifically not too fast. I think slow is fine. Like as slow as humanly possible is completely chill. But when you go too fast, you start getting into sort of special relativity. I think. I think that's where that one applies. Is like when you start approaching light speed, we tap out. Okay. So those are our sort of conditions. But for relatively well-behaved things, Newton's laws of motion apply. So what are they? Number 1. Terrible one. There we go. So some people say bodies of motion stay in motion. Some people say things unacted upon by a force will remain at constant velocity. But essentially, bodies at rest remain at rest unless acted upon by an external force. And the same can be said for in motion. Bodies in motion stay in motion. Which is basically saying that unless there is a force acting on the system, so unless I like poke something, it's just going to keep doing what it's doing. It needs... Thank you for the follow. Welcome in. It needs a sort of impetus. It needs an outside effect to then get like kicked out of whatever it's doing. The one I think you go to is the like, oh, you need an alarm clock to motivate you into getting out of bed, that sort of thing. But if you want like an actual physical example, things falling from a great height, there's this whole thing about terminal velocity, which we'll do later. But it's essentially like once gravity's done all it can to accelerate you downwards, you move with constant velocity and constant speed downwards because now there's no extra forces. The forces are all sort of balanced. And there's no new thing to change your acceleration. Which is why parachutes are good. I don't think if there are any others. Things in space. It's like the big cruxy. Where's my astrophysicists when I need them? Where's Thomas at? Unacceptable. There's like so many sci-fi movies that the dramatic point in the space movie is that they're floating in space and they need to let some air out and, you know, apply a force to them. Otherwise, they're just going to keep going in motion without moving. I think Thomas actually did a really good movie on video on The Martian. I think that's part of a plot in The Martian. Or it might be Interstellar. There's a lot of space movies and I really haven't seen all of them. Yeah. But that's picture in space, right? That it is The Martian. There we go. So you need to apply an external force, and in that case it was a bit of thrust to sort of affect your acceleration. Look at me remembering things. Was that the video that Thomas did for Simon's channel? Someone check that out. It was a good video, to be fair. Thomas Rintoul, Simon Clark. Shameless promotion of my friend's work, because my friends are really cool. So there. Okay, so Newton's second law, this is the one that we're going to use most today. Arguably we're going to use 3, but we're not going to talk about it as much. It's not as fancy. So the force acting upon a body. Here I'm using body in the same way that I would use like particle or like, it just means an object. It's not corpses. I don't know why anyone would think it would be, but that is where my brain went when I was learning A-level maths, and like, just want to clarify. Force acting upon a body is this is mostly like struggle in me remembering how to spell things. Equivalent to the mass of the body multiplied by its acceleration. Okay, so this is where F equals ma. Force is mass times acceleration. So the force is mass times acceleration. And we could take that as like the definition of force. If we know the mass and we know the acceleration, we define the force in that way. You could also say that it's the rate of change of momentum, I believe. But we're not doing momentum till next week or the week after, so like, whap whap. Something similar in Gravity 2 and the Helping Hand episode Love, Death and Robots. A, Love, Death and Robots, freaking excellent shout out. B, yeah. You're in space, there's not much else you can do to be dramatic. Ah, it's in an episode of animated space show Amazon Prime, I think. It had a green squishy alien thing and David Tennant voiced the bad guy. I swear there's a part of that show where they're floating and they need some momentum, just some acceleration in a different direction, and something happens. And what is that show called? That is gonna bug me to no end. It's like, it's not the Star Trek one. Final Space, I think. Yeah, Final Space. I think there's a bit in that show as well where they do it. Honestly, I think, can we just make a request for Thomas to just list all of the places where that trope is used in media, because it's going to be a lot. I don't know how many times it happens in Star Trek as well. I feel like a Newton's law counter for sci-fi would be quite fun. Someone will tell me that it's everything all of the time, but oh well. Anyway, what was I saying? F equals ma. Ta-da. This is the thing. This is the big one. if in doubt in a mechanics exam, or if you're doing any sort of question, just start resolving forces. And it'll probably help. It'll probably help. So yeah, this is the one that we'll probably see the most of in its outright equation form. However, we're going to make a lot of However, a lot of the times we are just going to assume Newton's third law. So the third one is two bodies exerting force on each other will exert, don't know why I put a Q in that, equal magnitude and opposite direction. Which is an awful way to say that, in my opinion, so I don't know why I wrote it that way. Let's see how other ways we can phrase this. It's essentially saying, if I push on something, so my hand's pushing on each other, the force that this hand feels from this hand is the same as the force this hand feels from this hand, but acting in opposite directions, because this hand is feeling a push that direction, this hand is feeling a push that direction. It's the same force, but from the perspective of each of them, it's opposite. So this is the one that is quoted by Live, Laugh, Love posters. For every So for every action, there is an equal and opposite reaction. Which, yeah, you could take into a karmic... what am I trying to say? Justice? Like karma, I guess. But in this case, we're talking about forces. Hello, welcome in. So... yeah, this one is really well known, maybe less as like a Newton's law, but we're going to see it a lot. And basically what I mean by we're going to assume a lot of this is when we talk about things that are touching, so two bodies, so a box on a surface or an inclined plane, or two things next to each other, anywhere where there's contact between any of the things that we look at, we're going to assume reaction forces are there. And I did, in fact, do a little bit of history. So we can cite these in the Philosophiae. So these are where they were first written. Hello, Cap. How's it going? So yeah, these are Newton's 3 laws of motion. Specifically, I'm sure he has other ones somewhere. Bodies at rest remain at rest. Bodies in motion remain in motion unless either is acting upon by an external force. So that's our sci-fi trope. F equals ma is our big equation. And our Live, Laugh, Love poster is for every action there's an equal and opposite reaction. So if you can't remember Newton's 3 laws, sci-fi trope, famous equation, Live, Laugh, Love. I feel like that's you know, a completely respectable and professional way to remember them. Makes sense to me. So, as I said before, with we are going to just look at F equals ma again because it is such a cool equation. So if a body has no mass, thank you for the follow, welcome in. If a body has no mass, we can't act a force on it. Okay, because if m is 0, then F is 0. And at the same way, if things are moving in constant motion, so that was bodies in motion stay in motion, and bodies at rest stay at rest. So if their acceleration is 0, and I've also committed a cardinal sin of mathematics, this is a one-way implication. If A is 0, then F is 0. Okay, so if there's no acceleration, there's no force being acted on it. If F is 0, either m equals 0 or a equals 0. So we can't say backwards and forwards, although if we're talking about something that we know has mass, so we know it's a box that weighs 5 kilos, and we say the force is balanced completely, we know it's either going to be in constant motion or at rest, right? There's no acceleration. Yeah, similarly, if it's feeling a force. I don't know what the other one would be if something had no mass but still had acceleration. I suppose it would be a direct proportionality. I think this comes up in a later question we've written, so we'll have a look there. And then the other thing, just as a reminder, so we measure, now let's do this down here. So we measure force in newtons. So I'm going to be seeing things like, e.g., 5 newtons. So newtons are the unit that we use for forces. They are named after Isaac Newton. And we'll be like, Kat, what are they? Well, if you were watching our intro lecture, all which you can go get on YouTube now, it's on YouTube, you'll remember that we can figure it out from looking again at this equation and remembering that that has units of kilograms. So mass is measured in kilograms and acceleration is measured in meters per second squared. So that gives us that 1 Newton is 1 kilogram meter per second squared. So it's a, yeah, kilogram times meters over seconds squared. Don't know why you'd want to use this immediately, but if you're checking equations down the line, it's really useful to know what units you ask if you need to check side by side. Hello, maybe dumb question, but is wind an example of something that has no mass but has acceleration? Yes. No? Wind has mass. But like what? I suppose, yeah, air has density, so it has mass. I think the like acceleration with no mass would be things like in an equation or like in an exam question, when you're given that something is light, we assume that its mass is 0. So like you might see things like a light inextensible string. That feels tension, so it's under force, but we impose it has no mass. So we say it has no mass. It does, but we pretend it doesn't. I don't think there's any real-world reason or real-world example of things feeling force without mass. We're doing maths. Mechanics. It sits between the two. Silly inaccurate paper question. Yeah, it's one of those like, because I think that's literally the example we have later, is like we have a light inextensible string, so technically its mass is 0, but it does undergo acceleration because it is moving. Basically, we make everything unphysical and then pretend it's real. I don't appreciate this math slander that is happening here. I mean, put a load of equations on the board and just because I can. Okay, yeah, so we measure force in newtons, and Newton is a kilogram meters per second squared. That's a mouthful, so we say newtons instead. photons are something with no mass but acceleration, though there are arguments. Yeah, and I think Newton's laws don't apply to photons, because going back to that too small and too close to the speed of light thing. So assume at the minute, if F is 0, it's probably not moving rather than it has no mass. That's the, like, for the cases we're looking at, that's the bit that makes sense. All quiet now? No, don't worry about it. Don't worry about it. Welcome in, everybody. Also, hi. Also, hi. Hi. Lost my head. Types of forces. So, I already mentioned one earlier with my example of Newton's first law. Sorry. Yeah, we've already seen one example. I said thrust earlier, where you have air being let out of a spacesuit to give you some push away. But there are a few different types of forces that we will see. There are probably more outside of this list, but this is pretty comprehensive for our purposes. Before anyone comes for me and I get another, you forgot my favorite insert thing. Turbulence is shit, okay? Deal with it. So, types of forces. Don't know what that was. May see include. So the first one that we will see is our normal, or sometimes called a reaction force. So this is from Newton's third. Wrote the wrong thing. From Newton's third law. So this is where things that are on a table, so for example, a box on a table, the box is going to experience a reaction force or a normal force to the point of contact. Thank you for the follow. Welcome in. Yeah, it's going to experience a normal force from the point of contact of the table affecting the box. Okay, so this might look like, if that's my box and that's my table, don't question it, it's going to be moving upwards. So just perpendicular to the point of contact. Although this one we are actually going to label R, because N is Newton's, and if I have NN, that's going to start getting really weird. Next thing that we're going to see is weight. So mass is sort of intrinsic to the dense, like how much stuff you have. And then its weight is specifically mass times gravity. So this will be different. I think I was going to write gravy. This will be different on different planets, obviously. But when you have a larger object, or if you have two comparable sized objects in space, like if you start doing planet things for whatever reason, there'll be more complicated gravity rules. But for the minute, this is the definition that we're going to do. And this one, we could either have just like an angle W, or we say mg. What kind of test is this prep for? Sorry, I missed that. So this is not really exactly prep. This is more looking at the mechanics that's taught for 16 to 18-year-olds in the UK. So loosely following A level, but like not fully comprehensive and not like in prep. But like the exam style questions that I've got for later, they all come from they all come from sort of undergrad level calculus, undergrad classical mechanics, A-level mechanics, A-level, that sort of stuff. Just studying Newton's law and making I just streamed it. Hey, welcome in. That was really surprising. I love that. So you're our expert in chat then. For when I inevitably make a mistake. Yeah, so we write this as MG. We might write this as W. And it always acts downwards in as much as it will act towards the Earth. But we can play around with what direction our coordinate system is in. So if we have things on an inclined plane and it makes sense to solve things aligned this way, we can do that. But we just need to be careful with where pointing down means. So that comes up a lot. One that was the bane of my existence at A-level, actually, is friction. I just really struggled with, like, understanding this, like, the equations and, like, the problems. I don't know why. Looking back on it now to prep for this, I'm like, this is quite chill, but maybe I've just made mistakes and the A-level trauma will pop back up. But friction is essentially resistance to motion. Resistance to motion. So typically this is from between two bodies. Just like Doctor Who, we should have a new word for gravity. I should be gravy. I will forget and get very confused is what will happen if we did that. Yeah, so you'll have a frictional force and it will move. Yeah, so opposes motion. Okay, so if we have something that is moving, say, box sliding down a rough inclined plane, it's moving that way with like 3 meters per second. Don't know what that was supposed to be. Then friction is going to be moving backwards. In the same way, if I push something, friction is going to be moving the opposite direction to the direction I'm pushing. It's resisting me. It seems the same to me personally, the setup as forces outside of math practice, so they're not forces. Oh dear. Okay. The other two that we're going to see potentially are tension, which is a pulling So tension is a pulling resistance of an inextensible string or rod to extend. So again, if I'm pulling in one direction, the tension is working opposite to me, and it's always going to be moving inwards towards sort of towards the center of say a string. So in particular, if you're thinking about we're hanging something from a string or we're pulling something with a rope, the tension in the string in the rope is going to be constant throughout, but at the point of contact is going to be moving away from it. So something under tension, right, is held taut. So it's being pulled at each end. And then sort of opposite to that, but not really. My spelling today is just like awful. Is then thrust. So this is now a pushing resistance to compression. So this might be things like a rocket, and then there's my rocket fuel. Don't question why my rocket looks like a house. This is a rocket. And then down here is the fire coming out the bottom, and then there's my thrust. Okay? What is a rocket if not a space house? Exactly. Here's my thrust. Okay? It's pushing, so it's pushing it away from the body due to some compression. So whether that's like combustion or I'm physically pushing, like if I do a press up, don't know why I would or could. That's an off-stream thing. I am pushing away. Technically I'm applying a thrust downwards that's giving me thing. Arguably that's more extension. Jumping, that sort of thing, where the body is detaching from wherever it was immediately before. But those are your typical forces. Okay, you've got thrust, tension, friction, weight. Weight counts, trust me. My scroll is not working and it's making me... okay, that's why. I need the mouse on the screen. That's really annoying. Wait, I'll put it there. Haha. Yeah, so normal reactions, weight, friction, tension, and thrust. So, kind of useful to just know about. I keep drawing them with arrows, and that is because we draw our forces using arrows to indicate direction and labels as magnitude. Okay, so what I was doing there where I was labeling them T, F, R, those are sort of the magnitudes, so that we would substitute that with a number. And then the direction that it's pointing is the direction of the force vector. So a force diagram might... Don't know why I stuck in capitals there. Might look like this. And this is where I realized that there's a lot of drawing in like this topic, and my drawing skills are like, I'm not gonna say questionable, but like they've been better, you know? So here we have a box on a rough surface on an inclined plane. So there's some angle of incline to the horizontal. We've got friction moving away from the direction of motion. So if there's no like impetus upwards, probably gravity is going to be pulling it downwards. We have whatever the mass of the box is acting vertically downwards because this is our down direction. So I would say gravity acts downwards. And then this is our normal or our reaction force from the box being on the plane. So this is the plane acting on the box. So these diagrams can get really busy. But just from looking at this, you can tell that this is a box sliding down a rough inclined plane. Okay, because it has that friction force, because it's moving sort of in that direction, we're assuming that's where it's going. It could be stationary. The forces could balance and it could be stationary, but typically this is what we're getting. But this drawing is, they can get really busy, right? Labeling. So drawing arrows on diagrams can get very busy. Cute triangle. Yes. Right angle triangle. So instead, we may draw. So I don't actually like these, but I know some people do prefer abstractifying. Abstractifying? Abstracting? Don't know. Yeah, so we may draw, and these are called free body. So instead of drawing the plane and drawing the box and drawing the angles and drawing everything around it, instead we just look at what if we're modeling it as a particle. So we draw our particle. So this is my box. And then I just draw in my forces. Okay. So you kind of you make it more abstract, and then this is with respect to a single body. So if you're doing a question where you've got connected particles or you've got multiple things going on in the system, you would draw multiple of these and sort of connect them together, which we will actually do later. So what's the sort of point of doing that? Well, the point is, right, when you have, I don't know why I said it like that. When you have all of these different forces acting on something, they don't necessarily feel each individual force or each individual component. Instead, they feel what's called a resultant force. So if I'm slowly pushing a box up a hill, right? R here is resultant. R here is reaction. So we have our reaction force, our friction force, and our weight, and they come from this diagram up there. Yeah, if I'm pushing a box up a hill, and say it's up a rough hill, right? So say something like this, there is going to be a friction force acting against me, and there's going to be reaction force, and there's going to be gravity. But if I am pushing it up the hill and it is moving, America, we use N for normal force. Yeah, so I saw that was something that people do. Decided against it mostly because A, I used R when I was in A level. It's what I'm familiar with. And B, if I end up doing something like F newtons, I don't want to, if I do normal force newtons, that's going to confuse me. So given that capital N is our unit, we can't use it anymore. It's been taken. Yeah, so if I'm pushing something up a hill, there are loads of forces working against me, but the overall effect is that the thing is moving. So the force, if I was just going to draw it as one vector, is upwards. So the overall effect. The overall effect of all the forces acting on a body. Thank you for the follow. Welcome in. Is called the resultant force. Okay. And this is just a single vector. So as an example, so we're just looking 1D for the minute. So say I have, thank you for the follow, welcome. Say I have a box on a surface, and don't worry about friction for the minute. Don't worry really about what's going on, but I have a body on a surface. I'm not even going to worry about the reaction force. There is some reaction force here going on. Doesn't matter too much. There's some mg. And I'm going to say that I'm pulling I'm going to say that I'm pulling this. So K for vectors be single even if they're dependent. I don't know what you mean by that. Yeah, so I'm pulling it with a force of 20 newtons, and I'm going to say that there is some force working against me. Maybe this is like a tug of war. 15 newtons. Okay. Then the box is moving. Yeah, so I'm going to say that the reaction force and the thing, because they're both acting on each other, we don't worry too much about them. So I'm just going to get rid of them so that we can look at the 1D example for the minute. Okay, so hello, welcome in. So tug of war with a box. Someone's pulling 20 newtons to the right, someone's pulling 15 newtons to the left. The resultant force is the sum of all of the forces. And this is a capital sigma, and it means sum of. So sum up all of the forces. Mai prynhawn dda, noswaith dda. How is it going, Flux? I always like it when you appear, I get more Welshy. So in order to sum things, we need to give them, obviously they're working in opposite directions, so we need to give a direction the positive. And I'm going to say it's that way. Okay, so I'm going to put my x-axis moving, and technically I shouldn't have put a y-axis there, so I've put my x-axis this way. So anything moving to the right is positive, and this is like standard convention. Typically y is up is positive, x across is positive. I do now wonder about in language systems that read right to left. I don't think the axes are flipped. There they are. To just wake up. It's late. It's quite late to be waking up. Concerning. Yeah, so we're going to say our x direction is to the right. Our positive x direction is to the right, sorry. So our resultant force, so I'm going to call this R capital F down here. So here we've got, so positive 20 newtons. And now the 15 newtons is working in the negative direction, so it's minus 15 newtons. So the resultant force on this object is 5 newtons. Okay? So that means that it's being pulled to the right with a force of 5 newtons, or it's feeling the overall effect of being pulled left and right is just a feeling of being pulled slightly to the right. That's a bigger force. I had a nap. Okay. Jeez, yeah. Completely reasonable then. Ready to see boxes fall down some frictionless slopes? Delightful. Okay, so that's a 1D example. What about in 2D? So in order to look at forces that move in, say, in 2D, I don't know why I'm trying to make this more complicated for myself. To look at 2D forces, we need to break them down so that we can compare in straight lines, essentially. So and specifically, we do horizontal and vertical because we say they're in their x and y. The horizontal and vertical y components. Okay? Because if we want to get all technical, this forms a nice basis, but this goes back to what I was saying about coordinates, where if we're describing things on the xy plane, and say that's our vector, it's got so much across and then so much up. Okay, so this is how we write it. So we do the same thing with vectors. Because they are directions and arrows, we break them down into how much they feel across and how much they feel up. And then because it's the resultant force, get this overall effect of being at an angle. So an example of this, if I have my particle and I have 5 newtons here and I have 20 newtons here, and I'm going to say that this angle is 30 degrees. You love vector math? Yeah, me too. Then first thing we need to do is define what directions are x and y. And because we have that 5 Newton aligned with our vertical, it's good to keep it in that direction. So for this problem, we're going to do x, y this way. And we could do it differently. But if we do that, we need to make sure that no matter which orientation of x and y we pick, everything lines up with one of those two, either in the x direction or the y direction. So looking at this, the 5 newtons we can leave alone because it's minus 5 newtons in the y direction. The 20 newtons we need to deconstruct. So this is where I said that like trig, so the 5 newtons x and y parts, right? Because it's 0 in the x direction and 5 in the y direction. So we need to do the same with the 20. So this is where that trig comes in. Thank you for the follow. Welcome in. So we have 20 newtons here, right? So we have a magnitude of 20. And we have an angle of 30. And I told you that an arrow is so much in the x direction and then so much in the y direction. And we do the same thing right over here. So we say that this is the x component of this vector, and this is the y component. And x and y are at right angles to each other. And then finally put in my 30 degrees. So essentially what I have is a triangle. I have a right angle triangle whose hypotenuse is 20 with an angle of 30 in it, and I want to find the other sides. Ad break? Yep, we'll do this and then pause. Because I need to stop talking. So we use SOHCAHTOA to figure it out. So x is, so if you haven't seen this before, these are saying that sine of an angle is the opposite of the angle over the hypotenuse, cos of the angle is the adjacent over the hypotenuse, and tan is opposite over adjacent. Because we have the hypotenuse, so this is the hypotenuse, opposite the angle is y, and next to the angle is a. So that gives us sine of 30 is opposite over hypotenuse, so y over 20. And cos 30 is x over 20. Page, that's why that wasn't going anywhere. So this gives us that the x part of the vector, the 20 degree at 30 degrees horizontal, the starting vector is 20 sine of 30, and y is 20 cos 30. Okay, and this is something that's going to come up a lot because we do inclined planes. Split it into, it's probably going to be one of them's going to be cos, one of them's going to be sine. Make a little triangle to draw it out. And then the other thing is we need to know sine of 30 and cos of 30. So my really quick way of doing this is if you draw an equilateral triangle of side length 2, split it down the middle, so this is side length 1. You've now created a right angle triangle where that's 30. That's 60. That is 30. And that side length is √3. So sine of 30 is opposite over hypotenuse. So this is 20 times a half. And cos of 30 is adjacent over hypotenuse, so root 3 over 2. One of those is much nicer than the other. Also, thank God you're a SOHCAHTOA person. One of my teachers used a different mnemonic for some reason. I'm curious what other mnemonics there are. Do I have a YouTube channel? This would be very helpful to many physics students. Oh, thank you. I, as of today, have a YouTube channel. It's posting specifically this lecture series up in VODs. And the idea is that once I start building, like just doing this at the minute is already scary for me. But once I start doing that, I'll put like condensed subsets of this topic, like really detailed, like specific questions is my plan. But yeah, it's Cat Does Maths on YouTube. Cat Does Maths everywhere, really. Okay, so this gives us our two vectors. So that 20 at 30 to the horizontal can be written in the x direction is 10 and 10 root 3 newtons. Thank you for the follow. Right, we're about to have an ad break, so I will be back shortly. And we're back. So, we broke down our 20n, and if you remember, this was the question that we were looking at, right? We had the 5 newtons downwards and then the 20 newtons. So the resultant force on this particle is the sum of these, right? So it's the 10 and the 10 root 3 newtons plus, right, now I wrote this as 0.5 and that was wrong of me. And if anyone caught it at the time and they're just like screaming at the VOD, good job. Because I said y was positive upwards, 5 newtons actually minus 5. So plus 0 minus 5 newtons, and that gives us a total resultant force felt of 10 newtons in the x direction and 10 root 3 minus 5 newtons in the y direction. I'm not going to figure out what that is to significant figures because I am not paid enough for that. We're leaving it still. Is there a MATLAB PTSD group I can join? I liked MATLAB. I don't know. The MATLAB hate needs to stop. I did a project where I used Python and I realized what I was missing. My next goal is to learn like a proper compiling language. No, not compiling language. I'm a sub pay you, so I demand you figure it out. How dare you? It's like, I mean, I don't know what root 3 is. Like, there is no way. Just programming language. What's the, like, compiling one, then? Basically, I need to learn C++ or C. One of those two. Square root of 3. Right, I think I saw a calculator somewhere. If in doubt, Casio from A level, and it still works. 10 times square root 3 minus 5. It's minus 5 plus 10 square root 3. This is the high level content you pay for, kids. Ah. There you go. Learn Golang. I don't know what that is. Java's not complicated. Compile languages are C, Java, C++, and Rust. Okay, I think I'm staying away from Rust. I learned Fortran 90 something back in the day. That was confusing. I had to go get a new calculator for uni. Oh no! I think I have like 5 or 6 of these lying around somewhere. You just keep acquiring them. Like every year you're a mathematician, a new one just appears in your house. Okay. So that's our vectorized form. But what if I want to draw an arrow? Okay, so that's still 2 vectors, right? If I think about it, what I've done is I've broken it down, and now I've said that there's a force that's 12.3 newtons up and 10 newtons across. And instead of that, I want to figure out what the result is. Because my resultant force is a singular force, and this is still technically 2. So if I want to do that, I would go back to my triangles. So my hypotenuse is always going to be RF. Now I don't know what the angle is, so let's call it alpha. X and Y are always at 90 degrees to each other, and we know that the X is 10 and the Y is 12.3. So we want RF and we want alpha. So easiest way to do this to double check it is, again, use SOHCAHTOA. And if I want the angle first for some reason, I can't use the hypotenuse. We don't know what it is yet. So we use SOHCAHTOA. We use TOA even. So tan alpha is opposite over adjacent, so 12.3 over 10, which is a number, 1.23. Don't know why I needed a calculator for that. Don't come for me. 1.23. We're trying. And that gives us that alpha. I made the mistake of mentioning coding, and I forgot that everyone in chat is computer nerds. I love this. Thank you for the follow. Welcome in. Any and all STEM or STEAM or art subjects are welcome. Okay, so the angle is arctan of 1.23. So that is going to give us an alpha of 50.8, which is actually 50.9 because I'm going to round up to degrees. Okay, so that is our angle. We could then use that angle, not just a computer, but also an aerospace engineer. You're going to fit in so well here. Yeah, that's not weird. We could then use that angle and use SAW or CA, use sine or cosine of the angle to figure out the resultant force. But the other way to do it is to look at the magnitude of the vector. So, which is basically just using Pythag again, actually. So if we look at this and we have a triangle. Thank you for the follow. So many new people today. I love this. Welcome in. Yeah, looking at the triangle. It's like a self-fulfilling prophecy, you lot. Yeah, looking at the triangle, the other famous Pythag theorem is a squared plus b squared equals c squared. So rf squared is 10 squared plus 12.3 squared. Rf is then the square root of the sides of the other side, 12.3. And again, I'm going to use a calculator. Square root. I can do 100. That's going to be like 144.9. 144.09. 151.29. That makes so much of a difference. Not even enough space for it. What? Oh yeah, it's not just 0.3 squared plus 12 squared. I committed that was a big mistake. Whoops. Right, square root of that. So 10 squared. No, square root, please. 10 squared plus 12.3 squared is 15.8, 15.9 newtons, 85 newtons. So if I come all the way back to the beginning of this question, here, my resultant force feels wrong Oh wait, no, yes. Would be here, and it'd be 15 newtons. And 50 degrees. Yeah. So that feels weird because it's not in between the two. It's not in between the two angles that were originally drawn, but if you remember, we broke that 20 into a vertical and a horizontal. So you had a lot of forces working in the vertical, and then you had some force working in the horizontal. And I'd made a mistake. There we go. Okay, let's just like red pen this because it's safer. When I came across here, from here to here, I swapped my x's and my y's. So the cos should have been the y, the x should have been the sine. The cos, sorry. The x should have been the cos, the y should have been the sine. Which means that this vector is the wrong way round. And it should be 10 root 3. There's nothing like marking your own work live on stream, you know? So this would be 10 root 3 on the top, and 10 minus 5 on the bottom. So the magnitude's actually the same. So it's still 15.9 newtons, but now those are the wrong way around. No, sorry. Not the same, because those are two different numbers. 10 root 3 and 5, not 10 root 3 and 12. That's 10 root 3, 5, which gives us Ah. 13.3 newtons. And this should be, so still opposite over adjacent, so 5 over 12.3. Sorry. 17.3. Which is an angle of 16.12 degrees. Which, if we then look at it, gives us something that is about here. And the that feels wrong. 19.9 newtons and 16 degrees. Hello, excellent timing. Cat's just making a mess. Can't I do a dot product where? Okay. Essentially, the methodology was right. We get points for method marks. We don't get marks for crossing between pages, which is the classic mistake that everyone makes, including me. So that's nice. Go team. Yeah. Run away from that and save. So compute. Lesson learned, get a bigger page. Yeah, if I could have like continuous scrolling on this, I think I would be much happier. To compute resultant forces, some So basically, you want to break it down into the vertical and horizontal components. And then trig. To determine magnitude. And what was the other one? Direction. So if things are aligned nice and neatly in just 1Ds, so just in the horizontal, just in the vertical, or they're opposite each other, you don't need to worry too much about direction. It's already done for you. If they're all at weird angles to each other, you break all of them down into their horizontal and continuous vertical parts. Sum over each of those respectively, get a nice single vector, so just one x value and one y value, and then use trig to find the magnitude and direction of that vector. And that gives you your resultant force. And check your answers. So that you do better than me. I was saying I want continuously scrolling paper, then I realized that stuff exists for a while. It's called a scroll. Yeah. Well, it does run out eventually. There's no infinite scrolling paper. So that's enough of that. Let's run away and pretend it never happened. Sorry. Let's talk about friction. So friction is a specific force that resists motion due to the roughness of a surface. Okay, you can't slide two things over each other. If you try and like slide your hands between each other, it heats up. That's the friction that you're feeling as it sort of like pulls against you. It can be a really useful thing if you're thinking about climbing, for example. You want loads of friction on that surface so that you have good grip because it's resisting you falling. In contrast, if you're doing something like table hockey, air hockey, you want basically no friction because you want the puck to glide really quickly over the surface. You want basically as minimal resistance as possible. And Cap, Goblin, lubrication in the way of a lubricant, so a thin film of a fluid, can be used to give that frictionless feeling. There's no such thing as a perfectly smooth surface in the real world. So the way we do it is by using, if you've seen like a ball bearing or like mechanics of bearings, they have WD-40. Yeah, exactly. If you want to glide something over a surface like a piece of paper, over a table, you use air. So you don't push really hard down on it. You kind of like let it slide. And what's happening is an air layer bounces between. If you wanted to, for example, bounce a droplet on a deep liquid bath for some reason, in order to get the droplet to move nicely over the surface, you would need a thin layer of air to do so, which is my research and why I'm saying that really smugly. So yeah. What were we talking about? I just got excited talking about my research. Friction. Yeah, comes up a lot in mechanics problems just because it's a really fun one. So if something is said that it is smooth, then no friction. If something is explicitly stated as rough, then yes, friction. So if something's moving over a rough plane, you're probably going to have to include the friction in the equation. If it's moving over a smooth plane, you're being told through the language that the question is using or the problem is using that you don't really care about friction. And things that are intentionally made very, very smooth by design for manufacturing processes are probably modeled as frictionless. Mass material presumably are important but not used in these cases. Yes, yeah. Sorry, just checking something. Right, we're gonna jump. Actually, I'm just gonna pause that because I want to do this. So let's explain how friction works. Then we've got exam questions left, so that'll be nice and easy. She says. So we quantify. So we quantify the friction through the use of the coefficient. Of friction. I remember this again, it was really like just wow, this I think it's because it's like typically used the letter mu for it. And when you're an A-level student, you're like, wow, Greek letter must be scary. Now less so. Also realizing that anytime we're like, we need to sort of quantify this, basically we just like, oh, it's coefficient of friction, it's coefficient of restitution. We just give it a fancy title and then it's basically just number in front. Remember your quadratic formula. X is what? Minus b plus minus square root b squared minus 4ac all over 2a. Your a's, b's, and c's in that are the coefficients of the equation. Just a fancy way of saying a number. And the reason that it's a coefficient is because the friction that a body feels is a coefficient times its, I'll write normal force. Okay, so F is mu r. In the case where that is a rough surface between the two things. So there is some more slight nuance to this in that, so if mu equals 0, then it's perfectly smooth. And we do actually put an upper bound on how much friction can be felt, because if I overcome the frictional force, right, so when it's 0, the two things are just kind of chilling there. They're not really affecting each other. But if it's starting to feel, so there's some motion, so say I'm like starting to push something, but that friction is bigger than me pushing, it's going to feel an increasing coefficient. So it's not necessarily fixed for the object, it's fixed for the situation. But if mu is 1, which is the maximum it can be, then it's the maximum friction felt. So for any pushing, E greater than so as soon as it overcomes the frictional force, it's able to move. Basically, I've maxed out how much friction can be felt, unless I start like pushing downwards, which is like sort of adding more normal force. It sort of maxes out. So that gives us that mu 0 is less than mu is less than 1. and they can be equal. But this is essentially when it comes up and you have like there's a rough inclined plane, or there's a rough surface and it's moving along it, or it's at rest but it starts to move or it starts to slip. The other forces in the system have sort of overcome mu r, and are now bigger than it, basically. So we're just going to jump. The angle matter, yeah, so the angles will matter when you have sort of where the forces are pointing. Right, we're going to jump into another little break because I can see an ad coming and I need to step away for a moment. Welcome back. First problem. A particle of mass 1.2 kilograms is held at rest on a rough plane inclined 30 degrees to the horizontal. It is released and then slides down the plane, moving 5 meters during the first 3 seconds of motion. Find A, the acceleration of the particle, and B, the coefficient of restitution. Not coefficient of restitution at all, coefficient of friction. Find A, the acceleration of the particle, and B, the coefficient of friction. I've written coefficient of restitution in my notes as well. That's something from my PhD that is just like stuck in my brain. Someone should really finish that comparison of what's on A-level in Northern Ireland, Welsh boards, English boards, and Scottish Highers. Was that a thing that I did? I don't think I did that. Someone should do that, because that would be really interesting to see. I know that there are like topics in A-level maths that are in exam boards in England that aren't in exam boards in Wales. They didn't used to be. Decision maths was not taught by WJC, which was interesting. Anyway, we have a question. It's really wordy. Let's try and get rid of all the words and just have a drawing. So, it's moving down a rough inclined plane. That gives me a triangle. 30 degrees to the horizontal, like that. I'll put my box here. Particle, but boxes are nicer because we do these little diagrams. Tried to start it years ago in Google Sheets, gave up, got ADHD. I have all of the maths, or I have a load of maths syllabuses downloaded for A-level. So it wouldn't be too hard if I find the Northern Irish boards and Scottish Highers. That would be cute. Yeah, when we have capacity. Cool. So we've got a particle. I'm drawing it as a box because I can. It's moving at an incline to the plane. So starting things off, we have our mg downwards. We know that there's some friction and it says it slides down the plane. So the friction is going to be working up the plane. We have our reaction force perpendicular to the contact between the particle and the plane itself. So first things first is I'm noticing that R and F are in this nice angle. So what I'm going to do is I'm going to sort of deconstruct my angles into vertical and horizontal from the frame of reference of the plane. So I'm going to say X moves up the plane and Y moves perpendicular to it. So you like tilt your head and then you're like, oh yeah, that's X and Y as they should be. Thank you for the follow. Welcome in. And consuming some capacity. Yes, yes. More things will happen. Hopefully by the end of this week, but then I'm away for conferencey things. So maybe the new year is a good time for new things. You study this in physics high school? Yeah, probably. It branches a load of different levels. And this is like a classic problem. So let's do the free body diagram as well, because this will hopefully help us break it down into our X and Y components. So we have F moving that way, we have R moving that way. We need to break that mg down. So if mg is here, then that is going to be, the angle is there. So the one touching it is going to be cos theta. And then down the plane is going to be sine theta. So let's just put that there, out of the way. So we have working opposite to the reaction force, we have mg cos theta. And then moving down the plane, gravity pulling it downwards is mg sine theta. Okay, so that's our free body diagram of that particle. Fourth playthrough, geez. That's mad. So that's our diagram, that's our problem. We've then been told that it moves. So it slides 5 meters during the first 3 seconds of motion. Okay, so we have a distance that it's moved, 5 meters. We have a time, 3 seconds. It started at rest, which meant that our u is 0. And we need to find some acceleration. Thank you for the follow. Welcome in. That to me is looking an awful lot like SUVAT. So from yesterday, not from yesterday, from last stream, from last lecture, we did kinematics. And in that, we had equations of motion for rectilinear motion, right? When there's constant acceleration. I'll tell you now that all of this is rectilinear. So A, and this instance is constant. So we can use our SUVAT equation. So we don't have a final velocity. We don't know anything about the velocity of the thing after it's been set loose. We don't know how fast it's going. So we need the equation that doesn't have v in it. And that is S is ut plus half at squared. For completeness, always try and draw gravity in the direction it's going in your diagram. So we said that u is 0, s is 5, and it looks like 5, so that's nice. 0 times 3 plus half a times. Thank you for the follow. Welcome in. Yeah, so 0 times 3 plus a half a 3 squared. We get 5 is 4.5a. I'm now doubting every bit of maths that I've known. Yes, that's fine. Why am I using x for multiplication? Because if I did dot there, then that would be 0.3. So I'm trying to be aggressively like, this is multiplication. Also discounting thermodynamics. Yes, they're definitely discounting thermodynamics and air resistance. Disregard air resistance. So that gives me an A as 0.9 meters per second squared. Okay. Dot in the middle of the line, decimals. There are no lines. Tell me, right, fucking fine. Better? Yeah, I agree when things are typeset, but when my handwriting goes like up at all angles, I feel like imposing, oh, it's on the bottom of the line, not in the middle of the line. I mean, I could... Ooh. Someone made the mouse slow, don't like it. There we go. Like, put really faint grid lines on the... I can make it dotted. I don't even think you can see that. Oh, we could put staves on it. Is that better? We'll write on sheet music. I'm now just playing ruled with a vertical line. Delightful. Where did it go? Where did... Right, let's put that back and then not touch it. $1.1, sorry. I did 4.9 divided by 5. Okay. Stop distracting me. 5 divided by 4.5 is 1.1 recurring. meters per second. See, now there's another dot. This is infinite dots. Now, that gives us our acceleration, which I'm just going to call 1.1 to 2 dp. Okay. Then part B of the question was find the coefficient of friction. So for that, we need to start doing something with this diagram up here. So resolving in the vertical direction, vertical to the plane, we have that the forces balance. So R is equals to, or technically, the force is balanced because the acceleration in the vertical is 0. So we'll write it out properly. So we do F equals ma. In this direction, the acceleration is 0. Acceleration is only moving down the hill. Thank you for the follow. Welcome in. So we get F equals 0. Now what is F? So positive is upwards, so that's R. And then downwards is negative. So that was that mg, and I'm going to quadruple check I've got the right one. Cos theta equals 0, which gives us our resultant force, or our reaction force, our normal force, is mg cos theta. But we know what my m is, and we know what g is, and we know what cos theta is. I'm going to leave the g's alone because multiplying by 9.8 is awful. So that gives me 1.2 times g times, right, cos of 30. Yeah, which we did before, and it was root 3 over 2. Yeah. So root 3 over 2 times 1.2 is 3 root 3 over 5. And you can tell that I made these questions because resist joke, don't, what? And that's in newtons. So G here could be 9.8, it could be 9.81, it could be 10 if you're wrong, but whatever sort of degree of accuracy you want to use for gravity, but we'll just leave it as G in terms of G for the minute. Okay, so that gives us that direction. We now have the direction pi squared. Like, at least it's more complicated than just like G is like 1, because why not? Okay, in line with the plane now. So we have F equals ma again. We know that the right-hand side of this equation now has value because we just worked out what the acceleration was. So we have 1.2 times by 1.1. That looks so awful to me. I hate it. I hope you're happy with yourselves. And then on this side of this piece, we have that positive is up the slope. So for some reason, we've decided that's the direction that's positive. So we have F minus mg sine theta. As long as we're consistent, it's fine. So F minus mg sine theta. So we have our frictional force is mu r. Minus mg sine theta equals ma. I'm just going to write it that way for the minute and then put it down. So we have mu times 3 root 3 over 5 minus g. 1.2 g times, so sine of 30 is then a half. And then we worked out, 1.2 times 1.1. So we get mu 3 root 3 over 5g equals 1.2 times 1.1. 1.32 plus now 0.6g, I think. And that gives us a total value of mu as 1.32 plus 0.6g all over 3 root 3. This is awful 5g. And I'm just going to say that if g is 9.8, because that's my preferred number, 1.32 plus 0.6 times 9.8 over 3 root 3 over 5 times 9.8 is a coefficient of restitution, or a coefficient of friction, sorry, of 0.71 to 2 dp. So there we go. It's a little bit disgusting because I came up with the numbers, and of course I did. But yeah, so if you wanted to work out coefficient of friction, you need to figure out, you balance all of your forces in F equals ma, using the fact that the acceleration in the vertical is 0. So these forces don't balance out. The force up is the same as the force down, which is technically already true from Newton's third law. But it's always nice to show it using Newton's second. Thank you. Yeah, so that's how you'd go about solving a problem like that. Things might get more complicated. They might, typically other types of questions like this you might see might involve things that aren't moving but are just at the point of moving, at which point you have maximum friction, or a force is slowly applied until something happens. Making my brain here. Oh, I think it's going to be analysis means maybe even more fun though. I mean, as long as it's either educational or entertaining or both, I think I'm doing my job. I think that's the goal, is like somewhere between those two, of putting out content that people want to watch, and maybe picking something up along the way. We started up the stream off with the live, laugh, love of Newton's laws, so it's all good. Taking dynamics class for third time this semester, this stuff is really difficult. I mean, yeah, this is stuff that I have done myself and then spent many years sort of studying the extensions of this stuff and then also teaching it. So I am moving through it at a quick pace because live streaming, unfortunately, is not super well built for in-depth, high-level content. Instead, this is more of a sort of broad overview of these sorts of things. So don't beat yourself up at all. But if you do want to watch back the VODs and then every time you get stuck, go and research what that little bit is, that's all totally fine. In fact, actively encouraged, because there's a lot of other content out there that did not take anywhere near as many pages as I thought to do. So, final problem. Using the diagram. Nice. Find the acceleration of the plate, the tension in the string, the magnitude of force on B by C, and the magnitude of force on the pulley by the string. So, I need to draw a diagram, is what I'm learning. Let's do that. We have an inclined plane. We love an inclined plane with 30 degrees. We have a block that weighs 5 kilograms. Question 0, find the diagram. Yeah. We have a pulley. We have a light and extensible string. We have a plate upon which rests 2 things. So this is block A, this is block B, this is block C. Oh, I'm writing behind my head again. My bad. So we have an inclined plane of 30 degrees. It is a smooth inclined plane. Okay. One end of a light inextensible string is a block A of mass 5 kilos, so 5g. The g is gravity now, it's not kilograms. It's not 5 grams, it's 5 times g. 30 degrees to the horizontal. The other end of the pulley, there's a light plate, so the plate has 0 weight, 0 mass, and then 2 blocks. I'm going to tell you that B has mass 3 kg and C has mass 10 kg. String plate made from photons. I mean, they're made from whatever maths teachers need to get equations out. Yeah, so this is all the information that you need. Presented weirdly. Aw, thank you so much. Have a great rest of your evening, and I hope to see you again in the next one. It is a light string. That is an awful pun, and I love it. So, this is our problem. We need to do these things. We need to find the acceleration of the plate. So it's just been released. We need to find the tension in the string. We need to find the magnitude of the force on B by C. And then we need to find the magnitude of the force on the pulley by the string. So I'm actually going to change color and I'm just going to start drawing all over this diagram. So we have one force downwards. We have one force upwards. We don't have a frictional force because we don't need one. So this is mg, remember. We have now tension because we don't have friction, but we have tension in that string. And that moves wherever the string is like touching something and then away from it. We have a reaction force of the pulley on the string, or the string on the pulley. We have reaction forces here and here, and this is why I didn't do this when I did it myself. So B on C, C on B, and then C just downwards. Where do you send misbehaving rainbows to prison? Don't worry, it's a light sentence. It gives them time to reflect. You know what? I'm quite impressed I haven't heard that before. Absolute chaos. Right, so this is disgusting to look at. So let's look at some free body diagrams. So on A, we have the reaction force, we have tension. So I'm drawing the forces, so those arrows that I just drew on block A, now in own space. And then I'm going to break down that mg again. So we just did it, so I can do it again. So this is 5g cos theta. Thank you for the follow, welcome in. And this is 5g sine theta. So on the pulley, we have our point, which is the pulley. So we have our tension working sort of down the string. And then we have our reaction force sort of moving in the opposite direction to those. On block B, so we have the reaction force with block C, and then we also have the weight of, sorry, that song really weirds me out. Block C, and then we also have the weight of it. So this is now 3g downwards. And then block C, we have the compression force from, so the reaction force from B is now working downwards because that's where those two things are contacting. And then you also have 10g. Yeah, that's everything. So as soon as it's released, the string and the platform all sort of move as one. Okay, the two blocks on the string, if the weights are distributed weirdly, it's all going to start moving. So looking at question A, Excel, find the acceleration. So we're going to look. So look at both ends of the string, okay? So I'm going to assume actually, I'm just going to say look at the string because that's okay. So I'm assuming you've got block A here, it comes down, and then it goes like that. And I'm going to assume motion in this direction. I don't have to. If I get a negative value, then we'll deal with that. But this is the direction that things moving. So this is positive direction down. Okay. So at block A, I've said that's the positive direction of that equation. So F equals ma. And now in this direction, I have the tension on the string pulling it upwards. And then I also have 5g sine theta, so gravity working against it to kind of counterbalance. So positive is t, and then minus mg sine theta is ma. And then at the plate, so at the other end, what do we have? We have tension up, and then we have the total weight acting on the plate downwards. So really, I should have done another one of these where you have tension up, and down you have the 3g from the block B and the 10g from block A. Block C, sorry. So F equals ma. Down is now positive because that's the direction of motion that I'm going to look at. So down you've got 13g, and then up you've got tension, equals ma. Okay, so I'm going to say the plate itself is light, but everything in it, so that whole object, the plate and the two blocks, are all one thing. So here it's 13g minus t is 13a. And then over here again, we have the weight of block A is 5. Sine theta, theta is 30. I really like 30 degrees for some reason. And I think it's because it gives me that this is a half. So it's 2.5g equals 5a. Okay, so I now have two equations and two unknowns. So I need to find acceleration and I need to find tension. So these are now simultaneous equations. So I'm going to label them 1 and 2. Okay, and I can basically get rid of the t in both of them and solve for a, and then get rid of the a and solve for t. So let's do 1 plus 2. So when we add equations, add everything on the left-hand side and then add everything on the right-hand side. So we get t minus 2.5g plus 13g minus t is 5a minus 13a. Okay. So cancelling this, the t and the t's cancel. So we get 13 minus 2.5, which should be 10.5. Yeah. 10.5g is 5 minus 13 minus AA. Okay. Oh yeah, plus. I don't know why I did a minus there. It's just like that. That's definitely positive. Yeah, you get... These numbers are disgusting. A is 1.3 G. The 2 decimal places. You do equation 1 plus equation 2, 18. Yes. As you can tell, I'm sleepy. Thank you for being here. If that was negative, would it mean acceleration was moving in the opposite direction? Yes, which doesn't make sense when I've got a 5 kilo block and a 13 kilo weight. It should go towards the heavier thing. But that is just me being silly. So we get, add everything on the right-hand side, add everything on the left-hand side. 13 plus 5 is 18A. So we get the A is 10.5 over 18G, which is 0.6G. Brain feels smart now? Good. I'm glad. So I'm going to do this, and I'm going to be really careful about it. So we have the A is 0.6G, and I'm going to do equation 1. So we get T is minus 2.5G equals 5A. Rearranging this then, you get T is 5A plus 2.5G. So 5A, 0.6 times 5 is 3. You get 3G plus 2.5G. You get the tension in the string. I'm literally using a calculator for everything now. I don't trust myself. The tension in the string is 5.5G newtons. 11.5? No. I think I'm right. And this is meters per second squared. Which, anyone was curious, this is about 53. We get a box of extra opposite that we lost a minus somewhere, so just take one from the box. I think we need one, to be honest. The amount of just getting confused with signs that happens is large. This is the risk of doing an evening stream where I need to use my brain. But that's half the fun, catching me out, I'm sure. Okay, so that's part A and part B, technically. So A gives us the acceleration is 0.6G meters per second squared. Always make sure that you include your units. And the tension is 5.5G newtons. Never do math while someone is watching. It's an incredibly humbling experience. Y'all are not scarier than first-year undergrads that think they know everything. Y'all are scarier than first-year undergrads when they have an exam coming up. Any of my first-year undergrads that still watch, I'm not sorry. I said what I said. So, part C of the question is the magnitude of the force on B by C. Now, there's this whole pulley plate thing happening, but B and C, the only really things that they're sort of inside of this contraption, right? So they're basically indifferent to the rest of the system. So the only thing that really matters is the reaction force of C on B. So everything's moving with constant acceleration. Thank you for the follow. Welcome in. So the force on B, so we want B's mass. We get 3A. And then the forces around B are, so mg, because it's just moving vertically. Remember, we have this sort of thing happening. So minus r. So this gives us that 3g minus 3a is r. So 3g minus 1.8g r. So the reaction force felt on B from C is 1.2g newtons. I did it right too and made a mistake. That's fair. I think this is an evening of we're chill, we're trying things out. If we make mistakes, as long as we catch them, as long as we sanity check ourselves, it's all good. Okay, and then there is 8 seconds before an ad break that I'm not allowed to dismiss, so we're just going to quickly jump to a BRB screen for a minute, and then you afterwards. Hello. It gave me a chance to stretch and sit down again, so hopefully everyone is nice and comfortable. I'm back from that. We don't control the ads control us, but we make do. Right. The only thing we have left in this problem is to determine the reaction force of the string on the pulley, or the magnitude of the force on the pulley by the string. So this is now... Hey! Thank you so much!
And it's me just subscribed.
I assumed it was a nightmare, but... please forgive Geraint's pronunciation. So, looking at the free diagram, you've got 2 tension forces, but they're the same force, and we now know what they are, pointing in 2 different directions, and then we have a resultant force, so the magnitude of the total force, right? Moving opposite. I'd still argue I'm a mathematician, but like I will concede if it means having more people around. So. Don't tell the mods I said that. Are they still here? They're going to shout at me. Hopefully they ignore me. So part D, we have T working downwards, working... No, you didn't. You heard nothing. You can't prove it. At an incline. So this incline corresponds to that 30 degrees earlier. Doing physics right now. This is mechanics. Applied math. I will concede applied maths. I definitely think I'm an applied mathematician. I'm not a pure mathematician. I used to really like number theory. It's been a while. It is interesting though, where you are in the world really shifts what subject you kind of fall under. Like I know that if I was in a university in the US, I'd be in a physics or an engineering department. Hands down. That's just where I would fit. But in the UK, applied maths is such a big thing inside of maths departments that like I can get away with liking this stuff and being a mathematician. So, nah. That was definitely directed at the mods, not at you, don't worry. Okay, we have this thing. We need to break it down into, we don't know what direction R is. But we know that these 2 forces are working sort of in angle, so it's going to be somewhere in between them. So this angle between the 2 is whatever's left from this triangle, right? We've got 30, we've got a 90, and then we've got the top angle. So this is 90 minus 30, which is 60. So if we wanted to do our force diagram here a bit better, to get the tension to line up in this direction, we'd need to kind of bring it to halfway, because it's going to be halfway between those 2 T's is where the balance of R is, right? Since they're the same force, the resultant effect is going to be halfway, which means that we need to bring it in 30 degrees. Remember, T works in this direction, T works in this direction. So in between them is 2T, and then it's touching, so it's cos 30. I'm going to make that arrow way longer so that I have space to write. And this is R. You're an engineering student. Yeah, welcome. See, this is what I mean. It's, we have, yeah, loads of different subjects all within sort of STEM that sort of overlap quite a lot. No! God damn it. For years I've been putting it off. If you really want to break everyone's mind, I work in a stats department. I'm technically hired by the Department of Statistics, just to add that one in the mix. So because the reaction force or the effect of the pulley on the string is the same as the string on the pulley, acceleration in that direction is 0. So we have that r is 2t cos 30. Remembering our geometry, our trigonometry, we got 2, we've got t, we've got cos of 30 is √3/2. So t is 5.5 g. So 5.5 √3 g, which is approximately 93.4 newtons, or 9.5. There we go. Why do you do this to me? Terrible. Absolutely terrible. Yeah, right. Summary with some random blank pages. We've been looking at forces and Newton's laws today. So there are 3 Newton's laws that govern motion specifically, and they only apply when things aren't too big, aren't too small. They're sort of Goldilocks size, and they're not too fast. First one is bodies at rest remain at rest, and bodies in motion remain in motion unless they're acted upon by an external force. This is our sci-fi trope, last hope, need to throw something away from me, even though that doesn't really work, attempt. This is our Newton's first law. The second one, the force acting upon a body is equivalent to the mass of the body multiplied by its acceleration. F equals ma. It's that if they're not saying E equals mc squared, they're saying F equals ma. Very, very iconic equation that we used loads in this. The final one is our live, laugh, love of our Newton laws. So 2 bodies exerting force on each other will exert equal magnitude and opposite direction. Or basically, for every action, there is an equal and opposite reaction, which has been used by people to describe karma. But in this case, it's just talking about normal forces. Nothing quite so dramatic. So these were discovered, written down by Isaac Newton. It's all right. He's a dude. Got some figs in Cambridge, I think. We then had an existential crisis about if a massless object could have a force and acceleration. But generally speaking, if the equation on a body that has mass has force as 0, the acceleration is 0, and that's where the second law sort of comes from, that bodies in motion stay in motion, bodies at rest stay in rest. The force is needed to change the acceleration, or to give acceleration non-zero. Real question, was Newton a physicist or a mathematician? He was a mathematician. I don't actually know how they classified it back in the day. He was probably a philosopher, because we were all researchers in sciences, were all sort of one big amalgamous blob until departments started being more and more of a thing. But I know that we call dibs on him. So, was Isaac Newton mathematician or a physicist? Was an English polymath, active as mathematician, physicist, astronomer, alchemist, theologian, and author. Basically like natural sciences. Everyone sucks except philosophers. Exactly. If the field of physics really... Yeah, they sort of studied everything, or they learnt to study. And it was assumed that, you know, this is why we have PhDs, doctorates of philosophy, is that it's sort of, you've thought about a lot of stuff. Yeah, basically. People didn't get really, really stuck on one specific subject back in the day. They just kind of did everything. Mathematicians can have Newton, the physicists can get lol. Okay. We talked about if the force is 0, either it's massless and things are getting scary, or the acceleration is 0 and it's at constant motion or at rest. We discussed the fact that it is a Newton is how we measure our forces. And then we talked about types of forces. So normal and reaction forces, basically the set thing from Newton's third law, how things affect on a table. We talked about the weight, and we kind of skimmed over the fact that I called it a force, but it is, sort of. Don't look too hard at it. And we spelt gravity as gravy. Fun was had by all. Frictional forces, resisting motion between two bodies. I don't know how else to describe that. Tension, and then thrust were the final ones. We talked about force diagrams and how they get really messy, but you're basically, you draw a schematic of the thing you're looking at and then chuck a load of arrows on it. And if it's way too busy, you do a free body diagram where you just do the arrows. We talked about the fact that you can have loads of different forces acting on a surface or on a body, and the overall effect of them is called the resultant force, and that's what you figure out when you kind of add all of the vectors together, is what's the overall effect felt by this thing. If I just want to draw one arrow on my force diagram, where is it? How big is it? So we did an example in 1D that went brilliantly. We did an example in 2D that went wrong, because Kat is bad at remembering how to be consistent. But essentially, the difference between 1D and 2D, 1D you sum up in one direction, 2D you break it down into the two directions, sum up, and then use trig to find the angle between them and the overall size, using the vectors. Little highlight from that then was break the vectors into vertical and horizontal components, try to determine the magnitude and direction using trig, and then double check your workings because you probably made a mistake. We talked about friction and how if something is described as a rough surface, there is a friction and a friction coefficient there. If something is a smooth surface, then there is no friction, and the friction is proportional to the normal force of the body. If you change the normal force, so by like smushing it or pulling upwards or applying some force in the normal direction to the contact, you're going to change the friction. Don't be prepared to be consistent, don't be mood. Typically, coefficient of restitution is bounded between 0 and 1, where 1 is sort of the maximum friction is being felt by a system. Then we did some exam questions. We had a thing sliding down a rough inclined plane, because I couldn't do a force topic without talking about inclined planes. And then we did another inclined plane, but this time with pulleys. And we had a smooth inclined plane, but now we had a pulley, and we worked out the tensions in the string. We worked out resultant forces on individual objects within the overall system, and then we looked at the magnitude and resultant forces on a pulley. So that doesn't sum up everything that you could ever do with forces and Newton's laws, but gives quite a nice little overview of everything. So next time, if I don't know why I opened that, that's not where it is. Where is it? Oh god. Ah! Panic. Everyone just panic for like a quick second while I find my list. Next time, we're going to be looking at moments and center of mass. So instead of things moving, things are going to be stationary, and we're going to look at moments about them. And if you don't know what a moment is, you'll find out in the next mini-series stream. So there.